Now the Earth is an irregular shape because of the surface, the oceans and mountains and gravity and so on. But we can use a mathematical shape, which is called an ellipsoid. Now an ellipsoid is a relatively perfect shape, which the Earth is not. So there was a survey done in 1984, and this survey was the WGS 84, and that's provided a basis on which we can then model the rest of the Earth. When you're dealing with GPS and so on, it will look at that. Now the Earth is a sphere, of course, so a sphere is round, a round object is 360 degrees. So we could describe the Earth as being 360 degrees round, which isn't overly helpful. We can subdivide that into 60ths. So each degree is divided into a 60th. So within each of those 360 degrees, you've got 60 minutes. So if we multiply 360 degrees by 60 minutes, we should get the number 21,600. Why is that useful? Because 60 minutes, 1 minute, equals a nautical mile. So 360 degrees, each one is made up of 6 nautical miles. It means the Earth is 21,600 nautical miles. Also, helpfully in the metric system, 40,000 kilometers. Lovely. Now that is at the equator. What is the equator? Well, the Earth is rotating, and it's quite useful to have a point at which it rotates. Let's call that point an axis. Now that axis isn't actually straight up and down. It is actually 23.5 degrees. I can only do 23 here. So it actually rotates on this wonky axis. We can call these the poles. So we can have the North and South Pole. Lovely. So we can now rotate about that point. We rotate in an easterly direction, which is also the direction that we rotate about the sun. This might be helpful to visualize it from above, from up here. Great. Around the axis, north and south poles. Now the angle is interesting because why? Well, let's draw another line in here just to demonstrate what up and down would be. I'm going to put this in yellow. So here we are, straight up and down. Now what could this represent? We will add on the sun, a particularly small sun for the purposes of this demonstration. As you can imagine, the part of the Earth here which is closest to the sun is going to be in daylight, and the bit furthest from the sun is going to be in night. Great, good and fine. Now we were saying that we wanted an equator. The equator is probably a sensible place halfway between the North and the South Pole. So let us draw on an equator highly manually like that. There we are, an equator. Quator. An equator halfway between the North and the South Pole. Superb. What can we do with this? Well, it's about halfway up. Let's mark that as our central datum. So I'm going to mark that as 0 degrees. Now we can add on some extra little bits of information here. This angle, as we suggested, was 23.5 degrees. So let's add on another line north and south of the equator at 23.5 degrees. 23.5 degrees. And we shall call this the tropics. And at the top it's Cancer, and at the bottom it's Capricorn. The interesting thing about these two circles, this 23.5, is that on the longest and shortest day of the year, the sun will be at midday over one of these tropics. So the longest day in the northern hemisphere will be over the Tropic of Cancer. Longest day in the shortest in the southern hemisphere will be over the Tropic of Capricorn. As you can see at the moment, the south is tilted towards the sun, and that will be demonstrating a southern summer. Now we can go a bit further than this. We can draw another interesting line on, which is going to be from this point and from this point. What might be interesting about that? You know it already. So this point, as you can see, is made up from the very top, and that is going to be a circle. And it's going to be the Arctic at the top and the Antarctic at the bottom. Whereabouts are they? Well, they are at 66.5 degrees, 66.5 degrees. What's special about those? Well, as you can see by the night and day line here, this yellow one, the whole of the Arctic Circle is in the dark. And however the Earth rotates about its 23.5 degree axis, it will remain in the dark. So this picture is therefore representing the shortest day in the northern hemisphere. Meanwhile, in the south, in the Antarctic Circle, you are, no matter how the Earth rotates about its axis, it's going to remain in daylight. So the Arctic Circle, the kind of definition of the Arctic Circle, is a place that on the longest or shortest day, respectively, the sun will not rise at all or will not set at all. So that's the circles. Happy days. Now the Earth does orbit around the sun on a plane of the elliptic. That's the orbital path. Elliptic. There we are. So that can also describe the relative movement of the sun in relation to the Earth, so the relative movement. And that's the same direction, that's an easterly direction, same as the rotation. Earth's equatorial axis inclined at 23.5 in the elliptic, as you can see by the angle there, and also the tropics. Now the inclination of the Earth, this 23.5 degrees, is what's responsible for the changing insolation over the surface of the Earth throughout the solar year. What's insolation? Well, the sun is obviously a lot bigger than this. So imagine the sun's rays coming across pretty much square on. Now, as you can see, at this part of the Earth, if you take a small sample, the sun is hitting pretty hard. Quite a small amount's pretty hard. If we take that same amount over here, look how much of the Earth's surface that's covering. So you can almost think about it as the Earth, when it's in winter, a large proportion of the Earth sharing the same amount of sun, and in the summer, a small amount of Earth sharing the same amount of sun. Now, the closer to the equator you are, the more balanced that is, so the more regularly you can allow for it being nice and warm. Superb. What else? The seasonal patterns. Again, we've got this angle, which means that you've got more time for the sun to be up, and the more energy it gets more of the time. So there's our seasons coming there, and of course also the daylight difference, as mentioned, more sun in the summer. Interestingly, the speed of change, the speed it gets light and gets dark, changes throughout the year. So the amount of twilight and the amount of between darkness and light adjusts throughout the year. Wonderful. Now, changing insolation throughout the year is a cumulative result of inclination of the Earth from the ecliptic, changing position of the sun relative to the surface of the Earth, and the changing distance of the Earth from the sun.